These brackets reveal a shift in mechanical engineering. In the left hand, a traditional, blocky machined part. In the right hand, a lightweight skeletal equivalent. They carry the exact same load, but their physical forms represent two different design philosophies. Engineering has followed a reliable sequence. Draw a basic starting shape, carve away material, and check the stress until the part works. But this shape then refine method leaves behind structural dead weight, metal that remains simply because human intuition didn't know how to safely remove it. That dead weight carries a systemic cost. In aerospace, every unnecessary ounce on a flying structure increases fuel burn over the lifespan of an aircraft. You are continuously paying to fly metal that serves no structural purpose. Generative design and topology optimization invert that entire process. Instead of drawing a starting shape, the engineer starts by defining a design space, the maximum volume the part is allowed to occupy, along with the strict physical constraints it has to respect. By setting up the boundaries first, an algorithm explores the physics of the problem directly. It discovers efficient, almost biological forms that a human working at a drafting table would rarely think to draw. The human engineer is still the one setting up the problem. They define exactly where the part must bolt to other components, the maximum forces or load cases it will experience. This digital design space highlights boundary zones for loads and supports. The software runs finite element analysis, scoring the block. Iteration by iteration, the algorithm strips material from low-stress regions, carving dead weight until it reaches a branching structure with minimum required mass. Marketing materials often label this process as artificial intelligence, but the engineering reality is mathematical optimization. Every curve and branch is driven strictly by the parameters the human engineer assigned. If you change the safety factor or the load direction, the resulting geometry changes completely. When executed correctly, the mass reductions are massive. General Electric once ran a public engineering challenge to redesign a standard metal lifting bracket for a jet engine. The winning algorithmic design dropped the bracket's weight from roughly 2 kilograms down to just a few hundred grams, an 84% reduction, while still safely carrying the exact same structural load. The technique also streamlines complex assemblies. General Motors used generative software to redesign a seatbelt bracket, consolidating 8 separate stamped and welded pieces into a single unified component that was 40% lighter and 20% stronger than the original assembly. The algorithm's true strength lies in removing our preconceived biases about what a mechanical part should look like. It optimizes purely against the physics of the load, leaving behind only the material that the math requires. However, finding that mathematically perfect load path creates an immediate physical problem. Topology-optimized parts are full of curved internal webs and blind cavities. You cannot put a block of metal into a standard milling machine and cut these shapes out. To pull these designs off a screen and into the real world, you have to pair generative design with additive manufacturing, industrial 3D printing. Because additive systems build a part layer by layer, they can construct complex internal geometries that traditional subtractive machining simply cannot reach. The result is a finished lattice of titanium or advanced metal alloy that can be lifted directly out of the printer's powder bed. The fine support struts underneath are then snapped away or machined off, leaving the finalized organic shape. For years, these high-efficiency shapes remained theoretical, confined to computer simulations. The practical application of topology optimization only became possible when additive manufacturing matured enough to build these geometries at scale. But printing a metal part introduces its own set of engineering hurdles. Additive manufacturing requires you to manage rough surface finishes, potential internal microscopic defects, and the residual thermal stress caused by melting metal layer by layer. Because of these variables, an optimized geometry cannot simply be trusted because the algorithm declares it perfect. It must be subjected to rigorous physical testing on a metrology bench to prove it meets strict certification and fatigue standards. When those standards are met, the payoff is real. Airbus successfully qualified a generatively designed bionic partition for the A320 cabin. Because they navigated the strict aerospace certification process, that single weight reduction, when scaled across a fleet, translates to massive annual carbon emission savings. To get a part to that stage, engineers have to meticulously ground truth the physical part against the digital model. They manually measure the wall thickness of the thinnest organic webs to guarantee the printer actually delivered the dimensions the simulation relied on. The raw output of a topology optimization is best understood as a highly educated guide. It narrows the search space for the perfect part, but it does not retire the responsibility of physical validation. Ultimately, generative design produces options. It provides an analytical trail where engineers evaluate columns of mass and peak stress values across dozens of iterations, manually hunting for the specific candidate that balances safety, manufacturability, and lowest weight. Trusting a pretty skeletal result without double-checking the underlying assumptions is dangerous. If the human engineer misses a critical load case or sets a factor of safety too low in the initial setup, the software will generate a structure that is unsafe in the field. Generative design trims the weight that traditional methods leave behind. It explores geometries that humans wouldn't think to draw, but its effectiveness relies entirely on the discipline of the engineer setting the boundaries and verifying the math. To explore the exact mechanical constraints and load cases that drive these algorithms, click the link on screen to access our full technical breakdown of generative engineering.